So more formally, S of t is the stock price at time t, and this is a model that tells us what happens to that stock price as we move through time. ds is the continuous version of delta s. In other words, it's the instantaneous change in the stock price, in the same way that you can think of a derivative like ds dt as the instantaneous change in a stock price. This isn't exactly equivalent to a derivative because, as we'll see, we're going to be assuming that stock prices satisfy a property that provides a lot of variability in the stock price, and that while the stock prices that come from these models will be continuous, they will not be differentiable. We will not be able to calculate derivatives of these stock prices that emerge. However, we can think of ds as an instantaneous change, somewhat like a derivative, but again, recognizing we can't quite have a derivative with these models. Alpha is a compounded, continuously compounded expected return, as it's been before. Sigma is the continuously compounded return volatility, standard deviation, or volatility. Zt is a normally distributed random variable. We'll see in a moment that z of t is a normal variable with a mean of 0 and a variance of t. And dz is sometimes called Brownian motion, and it is, in essence, the instantaneous change in a process that has the property that at each point in time it's a random variable that's normally distributed. So we'll need to study what that means a little bit more. As I mentioned a minute ago, the process that was identified in Formula 20.1 is called geometric Brownian motion, and that an expression generally of the type that we see in equation 20.1 is called a stochastic process. So a stochastic process is one in which one identifies the change in the stock price, a ds, in terms of a drift term, might be some very general function alpha, which might be a function of s and t, and that's a drift term times dt. And then one might have a very general volatility term, sigma, could be a function of s and t, and that's being multiplied by this right now mysterious dz term. So there are two important implications of this equation, and the justification for this will emerge as we develop some additional mathematical tools to deal with this result. The first is that if we assume that the stock price today is s of 0, then we can identify the probability distribution of stock prices at time capital T for any capital T. And in particular, what we find is that S of t will be log normally distributed. You remember what that means. If we say that S of t is log normally distributed, that means that the logarithm of S of t has a normal distribution. And when you, and this is something that has been alluded to in prior modules, where after some work with our binomial distributions, the point was made that the distribution of stock prices from a binomial distribution, while initially binomially distributed, has the property, the way they were developed, that when h, the time interval in the lattice or the tree, converges to 0, the probability distribution of stock prices at every point in time in the future converges to a log normal distribution. This is indeed that log normal distribution that those binomial lattices converge to. And what one, or it's similar to, and the reason it's not quite like that is that here we're dealing with a stock process that has a general return of alpha. And when we construct our binomial lattices, the alpha will be replaced by an r, or an r minus lowercase delta for the continuous stock dividend. But otherwise, this is the log normal distribution anticipated by the limit of those binomial distributions. And notice the parameters. First of all, of course, S of 0 plays a role. You have to start somewhere. That's part of the mean of the distribution is its initial value. The continuous return alpha plays a role. And notice this recurring minus a half the variance. And this will come out of, ultimately, Ito's lemma when we develop that idea. But there is an adjustment to the mean. When we go from geometric Brownian motion with alpha being, we will see soon, the instantaneous continuous return of S, that when we look at the log of S, the mean of that distribution has a shift below alpha. And the amount of shift is exactly a half sigma squared. And of course, as always, both the mean and the variance of this distribution are proportional to time. That the further we go out in time, the more the mean drifts and the more the variability of that normal distribution expands. Geometric Brownian motion provides more than just this terminal distribution at each point in the future. Stochastic processes are useful because they also allow us to think about the path of stock prices that are followed from time 0 to time t, and allows us to generate sample paths, a variety of sample paths from time 0 to time t. And you recall from the chapter on exotic options that, in fact, there are many options whose values are path dependent. So one would have no hope of valuing such an option unless you could develop a model which explicitly recognized what the paths of stock prices could be, and consequently what the value of those options are on those paths.